So they say you can't step into the same river twice, and still we learn from experience. So for instance, I learned from this trip that I'm showing you here that I like going upstate in the fall, that Bergen County, New Jersey, if you didn't know about it, is a surprising treasure trove of easy and pretty trails, that my son loves to touch water no matter how freezing the temperature is. So what does all that mean? What does this learning mean? It means that in future situations, which will definitely be different from this one, I may draw on this experience in order to make decisions. And so one way to think about learning is that all of learning is generalization from past experience to different future experience, which means that a central question is, how do we set the boundaries of generalization? How do we decide what experience to draw on to make my current decision? So today I'm going to tell you some things that might seem obvious, but took me many years to realize through a lot of research by amazing people in my lab. You saw our picture up front. So a combination, our research is a combination of behavioral and neural experiments in humans and animals, and a lot of computational modeling. But the modeling that we do, so in my view, in general, the goal of computational modeling is to understand basic truths. So today I'll show you only the results of the models. I won't show you the models themselves. And I'll show you how we tested these results and these hypotheses in behavioral experiments. And to kind of tie to the introduction that you just heard, this is work done in my lab in the last 12 years that we are now taking to a new direction to look at mental health. So I'll finish with some of that, but I'm very excited about those new directions. So the main idea that I want to convince you of is that our brain is a categorization machine with an unlimited number of categories, and this is what we do all the time. So we take experiences as they come at us, or as we experience them, and we group them by similarity. We create these categories or clusters, or I will call them latent causes and explain that later. And we use these groups both to determine generalization boundaries in learning, what should I learn about together, and what should not interfere with something else, and also to organize our memories. So today, first I'll talk about how similarity sets the boundaries of learning, and I'll show you an experiment there. I will then extend this to some more real-world learning and social evaluation. After that, I'll discuss how similarity, or should I say dissimilarity, affects the organization of memories. And finally, I'll talk about how we can use this understanding to optimally modify unwanted or maladaptive memories, and this is where I'll start linking to mental health. So let's start. So part one. And I should say, if you have questions, you can raise your hand or use the buttons or the different equipment that you have here. You don't have to wait till the very end. So the first part, similarity determines the boundaries of generalization. So I'm stating this here as a statement, but really this was a question, a hypothesis that we had. And to test this hypothesis, Sam Gershman, who was a graduate student in my lab, did this experiment that I'm going to do on you right now. And the question is, so we showed subjects displays like this with a lot of circles, and we asked them to tell us quickly, in under 5 seconds, how many circles do they see? So you can speak up and say, how many circles? 30, 45. Okay. 39. Let's do it again. How many circles? 60. The 60s were close, 61. So this was the experiment, and continued for half an hour like this. Very boring or very interesting, because you can get closer and closer to the truth. That what we were interested in here was not how people count quickly or even how people estimate amounts. What we wanted to see is how they learn from these actual numbers to kind of estimate the next amount, because the number of circles was drawn from a distribution that had a mean, that you could learn that mean. And so the mean for these circles that I just showed you here is, I forgot that the pointer doesn't work. The mean for these circles, for all trials that look like this, was 65. So this is pretty close to the mean.
Are you what we call appropriate technology?
I have long hands, too.
You have pre-morbid data on
We don't have other data on these subjects.
Let's hold
Yeah,
off questions
yeah.
actually to the end.
Okay, so as you saw in the two trials that I just showed you, there were two flavors of trials, and we didn't tell subjects anything about these two types of trials in advance. We just say your goal is to guess how many circles you see. But the trials were all the circles were either red or yellow. And these two types of trials came from two different distributions, as you can see above. So all the red trials came from a distribution with mean 35. So they had 35 plus minus 10 to 15 circles in them. And all the yellow trials came from distribution of mean 65. This was in one condition. So in one block of trials, subjects saw these two distributions, or circles from these two distributions. Then, without telling them that something has changed, we changed to a different block of trials. And in that block of trials, which I'll call here condition 2, the yellow circles are the same. They still mean 65, but the red circles are mean 55. And I'm depicting them here as yellow and red, but actually each block had two different colors. So they could be green and blue, they could be yellow and red. And subjects did a lot of these blocks. So about 18 blocks, half of them condition 1, half of them condition 2, intermixed. And they're always doing the same thing. They're just trying to guess how many circles they see. And so our hypothesis here was that if similarity determines the boundaries of generalization, in condition 2, where all the trials are very similar, subjects might ignore color and learn one big distribution here with mean 60. So they would guess something close to 60, regardless of the color of what they see, of the circles that they see. Whereas in condition 1, because the two distributions, the numbers of circles are different enough, we thought subjects would group them by color and learn separately a mean for yellow and a mean for red, or whatever two colors they saw. So what we did to test this is we looked only at the yellow circles, so the ones that always have distributions with mean 65. This is exactly the same in condition 1 and in condition 2, and we're looking at their estimate there. And what you can see here is in condition 2, their estimate is closer to 60, which is the overall mean, whereas in condition 1, their estimate is closer to 65, which is the true mean for yellow circles alone. So what we learned from this is that similarity, this seems to us to suggest that similarity determines the boundaries of learning because people are on the fly, not consciously necessarily, or in fact, I think they, well, okay, I can't say much about that because we didn't ask them, but anecdotally, some of them said they weren't even aware of the colors. But in general, what they're doing is they're trying to determine, based on the statistics of the environment, based on what they see in the experiment, whether all of these circles come from the same cluster, the same group, the same latent cause, or whether they come from two different clusters. And so when I'm talking about latent causes here, I'm referring to hidden groupings. You can think of it as a causal structure where all these red circles caused by the same thing as the yellow circles or not. You can also think about it as clustering due to similarity or clustering over time in different situations. But the idea is that as we experience the world, we automatically infer from our experiences these clusters and use them to organize our learning. And in inferring latent causes, I'm really thinking about how we learn the structure of the world. What things are caused by the same or different causes. And so if I go hiking again, I will expect, so these latent causes, apart from being a grouping of my experiences, they're also a basis for my expectations, right? So if I go hiking again, I might expect to have the same kind of experience. It will be fun to hike with my kids. My son will want to touch water no matter where we go. But under some conditions, I might generate a new latent cause and realize that things have changed. So in a couple of years, when my kids are both teenagers, they will not want to hike with me anymore. They will be complaining the whole time. They complain now too. They will complain even more, and maybe I will have to learn that going to Bergen County or going anywhere, in fact, with 2 teenage kids is a lot different than going anywhere with a 10-year-old and a 12-year-old. So thinking about this kind of real-life decision-making and learning, we wanted to test this hypothesis. So this hypothesis that similarity affects learning, we've tested it in many different ways. I'm not going to show you all the experiments, both in animals and in humans. But I'm taking it to the farthest extreme from what I showed you right now to convince you that this is a pretty general phenomenon and something quite fundamental that our brain does. And so looking at social evaluations, how we evaluate other people. And this is work by, I forgot to say before that the work before was by Sam Gershman when he was a graduate student in my lab. He's now faculty at Harvard. And this is work by Yunsun Shin, also was a grad student in my lab. She's now a postdoc at Yale. And Yunsun was very interested in the phenomena that in social evaluations there's a negativity bias. So negative actions that someone does, something that's negative in our view, those events loom very large. And the question was, why is that? And Yunsun had the idea that this might be because of phenomena, something like this famous quote, happy families are all alike. Every unhappy family is unhappy in its own way. And the idea was, what if we apply this idea to latent cause inference and think about this kind of quote or this phenomenon. So imagine a work colleague or a friend. They're mostly nice, they're helpful, but once in a while they disappoint you. Like once they failed to speak up on your behalf at a meeting, another time they spoke over you, and once you heard them gossiping about you when they thought you weren't within reach, within earshot. So these are all different events, and they're quite different. We can give them different names, these negative events that this person did. So maybe each of these events is stored in your mind under a different latent cause. So maybe this person is unreliable, maybe there's a gossip, and I forget what the third example I gave. So each of these is separately attributed to a different latent cause here, whereas all their good behavior, they're nice on many days, it's just, pleasant to work with them, well, they're nice, right? That's just one thing, one big thing that has many events ascribed to it. So if we store events in these groups, then what might happen is when I then ask you, well, how is this person? Is that colleague a nice person or not? You might look at all the latent causes that you have in your mind and say, well, 3 bad things, 1 good thing. Now, overall, not the best colleague. There could be better, right? Even though there were very few bad events and many good events. And of course, if you did this averaging correctly weighted for how many events are associated with each latent cause, you wouldn't make that mistake. But we were hypothesizing here based on many other aspects, many other situations where we know that the brain basically uses something like, Weber's law or a logarithmic function of, 1 is very different from 2, but 101 is not very different from 102. So these are a lot, but each one of these counts more than it should because each event here is associated with its own latent cause. So to test this, what we did was we asked people to look at different donations. We told them you're going to a university and you're collecting donations for a charity. And so for each person, they would see how much they donated. They would see it both graphically, the number of coins, and it would say there, Gregory donated 78 coins. And they had to, in order to get them to pay attention, and actually this is a pretty boring experiment, so we asked them to log on this line on the bottom, how many coins Gregory donated, and then they would see the next one, Thomas donated 168 coins. this is what they did for about 20 minutes, logging donations. Behind the scenes, there were two different conditions here across subjects, not within subjects. So in this condition, which I call sparse stingy, there were a few stingy donations, so below 150, and a whole bunch of above 150 donations. But overall, the average donation here is 150. In the sparse generous, it's completely mirrored. So there are a few generous donations. Most of them are more stingy than 150. Again, the mean is 150. And at the end of the experiment, what we ask people is, what was the average donation? That's it. And so our hypothesis is that if they're using latent causes to group all these trials together, but separate these trials into different latent causes, then they will guess something that is lower than 150 as the overall average in the stingy condition, and higher than 150 in the generous condition. And we did this in a whole bunch of experiments, manipulating the sparseness of donations in different ways. So here there are just few donations that are in the sparse condition, in the sparse side. Here there are the same number of donations in the stingy versus the generous, but these are more different from each other, and these are more similar to each other. So the idea is, again, because unhappy families are unhappy in very different ways, there are many more ways to be a bad person than there are to be a good person, then again, that would cause a negativity bias. But here, because we're testing a very general mechanism, we want to show that it can be both a negativity bias and a positivity bias, depending on where you put the sparsity here. And so I showed you here two experiments. In fact, there were 6. No doubt reviewers asked for some of them, but we started with 4. Reviewers asked for 2 more. And what you see here is, in all cases, basically, we find that the overall estimate of the average is biased towards sparsity and not towards density. So next time you notice someone gossiping about you, think about, maybe I don't need to think about this too much and group it on its own. Okay, so part 3. So I titled this talk Latent Causes, Prediction Errors, and the Organization of Memory. And so now I want to turn to the organization of memory and how this grouping of experiences by similarity affects how we organize memory. And our initial assumption here was that if we're grouping these events into clusters as we experience them, this is maybe also how we store them in memory. And so this is a simple experiment where we wanted to test this. This was done by Angela Radulescu. She was a research assistant in my lab then. Now she's starting her faculty position at Mount Sinai. So you can see how old this is. And Sam Gershman as well. And what we did here is we asked people to look at little line segments that had a length and an orientation, an angle, and we wanted them to memorize them. So again, in order to make it interesting, we asked them to predict the next line. So they draw it with a mouse. Maybe they draw this line, and then we show them the actual line. And the closer they are, the more points they get. And this circle here counts trials in a block. So now the next block, the circle moved a little. Please predict the next line. They predict, they get the true line, etc. And I'll take you all the way to the end of the block, predict the next line. They're predicting, they get the line. And now at the end of the block, we ask them to reconstruct from memory one of the first lines in that block. So this is a memory experiment. And they basically know this because they did many of these blocks. So after the first block, they already knew that there was going to be a surprise memory test at the end of the block. I thought I would do that. Okay, so behind the scenes, like in the circles task, there were 2 types of blocks within subject. And one type of block that I'm showing here, the gradual block, what we did was, so what I'm showing you here, each circle here is a line, and a line in the experiment, and you see the length of that line and the angle, the orientation of that line. And what you see here is that we're just changing the length of the orientation trial by a small amount, plus minus. So this is just a random walk. And this is what we call a gradual block, because all of the changes are small and the line is changing gradually from trial to trial. The other type of block was called a jump block. And in the jump block, it's exactly the same, except in the very middle of the block, there is one jump that's four times as big as every regular change. So here, the line is changing from a pretty short line to a quite longer line, and from about 45 degrees to something like 70 degrees. And behind the scenes, so this was the behind the scenes, and our hypothesis here was similar to what I showed you with the circles task before. We thought that in the gradual case, because of similarity, because all these lines are similar to each other, they would be stored together in one big memory trace. So you'd have kind of the episodic memory of each of the lines, but they would interfere with each other in memory. Whereas in the jump condition, we were hoping that the jump would be sufficient to create a new memory trace, a new cluster of information that would be stored separately. So these lines at the end of the block would not interfere with the memory of these lines in the beginning of the block. And because we're asking subjects to reconstruct from memory one of the two first lines, we hypothesized that in the jump condition, people would be more accurate in reconstructing from memory than in the gradual block. And we did control here for the overall distance from end to start. That's why this one is kind of much more windy. So that what happens in test is the subject draws a line, and that line has some length and some orientation. And we can literally calculate the distance of that line from what they were trying to reconstruct. And the smaller that distance, the better their memory. We can also calculate the distance from the last line that they just saw. And the smaller this distance, the worse their memory, or basically the more these last lines are interfering with their memory for the beginning. And so the overall result is, as we expected, that in the jump condition, the distance to the start is shorter, and the distance to the end is longer than in the gradual condition. So people's memory is better. People's memory for these new first lines is better in the jump condition. So one idea here that I started talking about before is that we can use these groupings and these clusters as a prediction for the future, like my prediction for my future hike with my sons. And so at every point in time, basically, the subject here is expecting a line that's going to look quite similar to the previous line that they saw. And you can think of this jump as a prediction error. So you see something that you did not predict. The dissimilarity is really an unpredictable event. So in some sense, what I've shown you so far is that prediction errors cause splitting of these clusters and inserting a generalization boundary. And what I want to talk about next is how exactly do prediction errors affect memory structure. And I'll show you a couple of studies where we looked specifically at reward prediction errors. It's prediction errors from getting an unexpected reward and how they affect memory. So these were studies by Nina Rouhani when she was a graduate student in the lab. She's now a postdoc at Caltech. And Nina was really interested in prediction errors and their effect of memory because there's a lot of data suggesting that prediction errors that are perhaps signaled by dopaminergic neurons in the ventral tegmental area and the substantia nigra pars compacta. So you see those two areas here in this brain here. So these areas. Dopamine prediction errors are projected all over the brain, but they're also projected to the hippocampus, a memory area. And so the question is, does dopamine affect memory in this way that a larger prediction error would cause stronger memory? So this is one hypothesis here. On the other hand, surprising events and unexpected events have also been associated with noradrenaline and with the locus ceruleus here, close by, but different, and projecting norepinephrine, noradrenaline, and also, in fact, co-releasing dopamine, and also projecting to the hippocampus. And what we know about noradrenaline is that it is, or that it accompanies surprise, whether that surprise is for the better or for the worse. So if you think of a prediction error, a positive prediction error of 50, or a negative prediction error of minus 50, so getting a reward that's 50 higher than what you expected or 50 lower than what you expected, both of those events would cause a noradrenergic burst. And so it might be that we'll see stronger memory both for negative prediction errors and for positive prediction errors if memory is affected by noradrenaline, or we'll see this asymmetric effect if memory is affected by dopamine due to prediction errors. So this is what we wanted to test. And I promised today only behavioral experiments, so I'll show you only behavioral experiments. In fact, we only did behavioral experiments here. What Nina did was this. She told subjects that they would be learning the values of 2 reward categories. And the reward categories were indoor scenes or outdoor scenes. So on every trial, they see a scene. So this is an outdoor one. And they see it for 2 seconds. And then they're asked, please estimate the value of this type of scene from the previous experience that they've had so far. So they put in a number from 1 to 100. And then we show them the reward. And so on and so forth. So they're learning from trial and error to predict these amounts. They're telling us exactly what they predicted, and we can calculate on each trial what was their prediction error, because we know their prediction, they wrote it here, and we know how much reward we gave them, so the prediction error is just the reward minus their prediction. And we do this for many trials, in many experiments. And so basically the structure was this. They learned about these 2 types of scenes in one context or one room, and then in another room. These rooms differed in how variable the rewards were, but in both cases, one category had a mean reward of 40 cents and the other had a mean reward of 60 cents. They didn't know this, but I'm telling you this. And to make this, again, to make subjects more interested in predicting correctly and in the experiment as a whole, whatever they saw, they got a fraction of that money at the end of the experiment. So these were real rewards for them. And then after a delay in which we asked them to fill all kinds of questionnaires about their risk attitudes and other incidental things that I'm not going to tell you about now, we gave them a surprise memory test. And the memory test was about these images. So each image appeared in only one trial, each specific image. So we're showing them an image and asking them to tell us whether it's new or whether it's old, as in new, they've not seen it in this experiment, old, they have seen it in this experiment. And so here are the results. What we found is that memory was better, both for large positive prediction errors and for large negative prediction errors, for items that had large negative or positive prediction errors. And this was true both in the high variability room and in the low variability room. Of course, the low variability room has fewer large prediction errors because there's less variability in rewards. So both large positive and large negative prediction errors enhance memory. So that's what I've shown you so far. But we also know from other literature and from what I showed you in the domain of learning that prediction errors also cause boundaries. So we talked previously about boundaries of generalization, but also we know from work by Jeffrey Zaks and work by Sarah Dubrow and Laila Davachi and many others that prediction errors cause us to make event boundaries. As we see as we see information as a sequence, we put boundaries and separate our memories based on prediction errors. So the question is, are these 2 effects related, and what is the neural mechanism here? And in order to study that, what Nina did is she gave subjects a similar experiment to previously, but now they're not making predictions. They're just watching scenes, different items in a sequence, and seeing the reward that's associated with each of them. So we said something like, you're auctioning off. I think the cover story was you're auctioning off paintings or drawings or like whatever photos. I think it was photos. You're going to see each photo and then see how much it was worth in the market. Once in a while, there might be changes because the market changes. So this isn't because of the quality of that image. We told them these are just changes in the market. You should look carefully because a portion of this, the amount of the auction will be your earning. So pretty boring. They're just looking trial by trial, seeing these items. And so we were especially interested in these situations where there's a large reward prediction error. So there's a small difference between 90 and 93, but there's a big difference between 93 and 10. And based on what I showed you so far, we can have two hypotheses for what is going on here. One hypothesis is that these large prediction errors enhance memory, and as I showed you in the previous experiment, because they're making an event boundary, right? So they're separating the memories of these images from the memories of these images, and that's why later we find better memory for this image, or better accuracy for this image. There's basically less interference, like in the lines task. But a different way to think about this is if you think of the memory itself, what I'm talking about here is, and for those of you who think in terms of attractor network, so I'm talking about making a new attractor that's farther from all the other attractors. But it could be that we're not manipulating, the prediction errors don't manipulate the distance, but just how strong that memory is, how well is it encoded. And so in that case, it might even be the opposite in the sense that we know that when an event is encoded, what came just before it and is still in mind is encoded together with it. So here we might get a strong connection between this image and the image that came right before it because it's encoded so strongly. So to test this, first of all, subjects saw 36 trials, 36 images where they saw the image, then they saw its value, and then we gave them a memory test because that's what we do. And specifically what we did was we tested for recognition priming. So recognition priming is this really cool phenomenon. So you know how those of you who are, as old as me, we used to listen to actual CDs, not just like, one song at a time on Spotify. So you hear a song and at the very end of it, you know what's coming next, right? So that's what recognition priming is. So if I ask you, is this image, when I ask you about this image, is this image old or new? That already brings to mind the next image that was in the sequence. And so when I ask you about this one, is it old or new, you'll be faster to say it's an old image. That's recognition priming. So the idea is that's what we do. So we just ask old or new as previously, but we're looking specifically at pairs. So we can ask about an adjacent pair, and we expect the reaction time to the second one to be faster because of priming. And when I say faster, I mean faster compared to something that's out of sequence. So asking about this one and then asking about this one. So I can compare the second in a pair, and in this sequence, I expect the second one to be faster than in this sequence. Of course, we ask about every image only once. But now the question is, what's going to happen for this pair? So for this pair with a high reward prediction error situation, it could be that we have an event boundary between them, and that broke the recognition priming, and the reaction time for this image will be just like baseline, as if they're out of order. Or it could be the second hypothesis that I showed you, that these are actually very tightly bound because of that strong memory. So we will see that the second one is faster, just like in the priming condition. And so that is, in fact, what we saw, the second of the two hypotheses. So we see here that the high reward prediction error events have fastest reaction time, and they're significantly, so this is reaction time here, lower is faster. So this is significantly faster than the out-of-sequence pairs or just an item, a high prediction error item on its own, not in a pair. And so this suggests that these items have an intact link to their direct predecessor. And we've replicated this more than once. We did because this was contrary to our hypotheses, because we were thinking event boundaries, right? Protection from interference. But we still felt like something is missing here, because I've talked so much about boundaries, and I've shown you in the lines test that there's protection from interference. So our next hypothesis was, what if the specific reward prediction error item is a special item that has special connections to its predecessors? But if we look across it, if there's a boundary somewhere here, not necessarily between these items, but somewhere across this high prediction error event there's a boundary, then we should still see that there is less interference between these two than there is between, let's say, these two. And that's the amazing thing about recognition priming. It seems like it's such a fickle effect, but it's actually not fickle at all, and it even works at a distance of 1. So we can test recognition priming. So testing this after this will be faster than an out-of-sequence pair. So we did the same exact experiment as before, but we're testing the +1s here. So we're asking this, is it old or new? And after it, this, is it old or new? And here we expect to see priming, so low reaction times. We're comparing that to an out-of-sequence pair, so this one, and afterwards this one. So same distance between them, but they're just not in the right order. And the real question is, what's going to happen across the reward prediction error? So this item and then this item. And here we were hoping that finally our hypothesis would show itself in the data, in that we would see no faster reaction time for this event, because there was a boundary, and I drew it here, but we know that's not exactly here. It's somewhere around here that separates these two memory traces. And luckily, that is what we got. So now the high reward prediction error is similar to the out-of-sequence and is significantly slower than items that have a low reward prediction error between them and are in sequence. So the final experiment that I want to show you is, can we use this idea of grouping by similarity to our advantage? And one type of learning that we really care about is learning about traumatic or maladaptive events. So, for instance, in fear conditioning, what you do is you train an animal to associate a tone with an aversive shock. So you can do that 3 times, and the animal will have acquired strong fear from the tone. So you play the tone, and the animal freezes. That is their fear response. And so we can think of that as a maladaptive memory, or like a traumatic memory, like in post-traumatic stress disorder, or like in a phobia. And now the question is, how can we erase this memory? Or how can we modify this memory? And in many experiments and a lot of neuroscience research, what people do is they do what's called extinction. So they play the tone without the shock many times, long enough so that the animal, or as many trials as needed so that the animal stops freezing. But the problem with extinction is it doesn't, so this is called extinction because the association between the tone and the shock is extinguished, but also the behavioral fear response is extinguished. But the problem is that this turns out to be pretty temporary. So for instance, if we test the animal, so in the test, again, they'll hear the same tone, and we'll test, are they freezing? If we test the animal in a different context, so in a different box, we'll see that they freeze to the tone again. Or if we test them a month later, we'll see that they freeze to the tone again. So over time, spontaneously, fear recovers. And if we give them a reminder shock, we can enhance that recovery. So a shock without a tone, just give them a shock separately and then test them. So here's one of many, many results from the Richardson lab. And here, rats that had a reminder shock versus rats that had no reminder shock. And you can see how much more the rats are freezing after they had a reminder shock versus if they did not have a reminder shock at test. So this is a problem because it suggests that we can't actually really get rid of that initial fear. And thinking of our framework here of latent causes, we can think of it this way. So the first 3 trials here of tone and shock were obviously, they're very similar to each other. They were grouped together. And one way to think of why extinction doesn't really work is that when the animal experiences tones with no shock, then they might just put those in a different cluster, put it in a new latent cause, because there is a prediction error here, right? The expected shock did not appear, and that causes a boundary of generalization. And that boundary of generalization means that everything that I learned from these trials of tone, no shock, does not affect what I learned previously. And that's a well-known thing that extinction doesn't lead to unlearning the old association, it leads to learning a new association. So based on our theory, we thought, what if we make extinction more similar to acquisition, basically making it similar enough so as to coax the animal to put all these new experiences in that old latent cause, that old cluster. So that is what we did. Sam Gershman in the lab of Marie Monfils at UT Austin, because we don't actually do animal experiments in my lab, did this experiment on rats. So in acquisition, they had 3 trials of tone and shock. And then in extinction, on the first trial, he gave them a tone and a shock. On the second trial, a tone with no shock. Then a tone and a shock and 2 tones with no shock. And another tone with shock and 3 tones with no shock. So he's basically slowly weaning them off the shocks in the extinction phase. And he compared this to another group of rats that we call this gradual extinction, and the other group of rats that got regular extinction. So acquisition, 3 tones and shocks, and then in extinction the next day, these were both the next day, just the same number of trials with no shocks at all. And we had a third group of rats that we called gradual reverse that controlled for the number of shocks in extinction. So these have 5 shocks, and the gradual reverse also have 5 shocks. But here, rather than weaning them off, things are getting worse and worse over time for this animal, for this whole group of animals. In the end, we had 9 trials without shocks in all 3 conditions, because we wanted to make sure that the animals freeze at a low rate, because what we're going to do later is we're going to test them either for spontaneous recovery a month later, so that's experiment 1, or for reinstatement, so giving them a reminder shock and see if there's reinstatement of memory the next day. So I'm basically going to compare their freezing in 4 trials in which they hear the tone and there is no shock, to these last 4 trials of extinction, and ask, are they freezing more or not in test? And in modeling work by Mingyu Song, who just graduated from my lab and is now working at Facebook, she tested our computational model that I didn't give you all the details for to see what would it do in this experiment. And we know that under a reasonable set of conditions, that model assumes or learns 2 clusters or 2 latent causes. So each color here is a latent cause for acquisition and for extinction. Whereas what happens in gradual extinction is, again, in the conditions here, it's not under any type of conditions, but under these conditions of similarity in the beginning to acquisition, and also a model that assumes that latent causes tend to stay on for a while, so a time-dependent model. In this case, we can see that both acquisition and extinction and gradual extinction are lumped into the same latent cause. And if they're lumped into the same latent cause, that latent cause has, yes, 8 trials with a shock, but it also has all these trials without a shock. So we're expecting animals to both decrease their freezing response, their fear response here, but also to not show any recovery of fear later on because there's nothing to recover. In this case, there's something to recover because the original fear is still intact. But in this case, it's really been diluted by all these no-shock trials. And this model in gradual reverse, what it does is it also infers 2 latent causes, one of them for all the shock trials and one for all the non-shock trials. Again, the non-shock trials are not interfering with the learning of the shock. And so, indeed, as we expected, we found in both experiments that animals in standard extinction showed a lot of return of fear, where animals in the gradual extinction did not. So this is not significantly different from 0. So again, this is the amount of fear shown, the amount of freezing at test versus at the end of extinction. And this was true in both experiments. So to summarize, what I'm suggesting here is that when we think of learning something new, and this is kind of important for real life, when we think of maximizing learning, and when we're trying not to just learn something new, but to unlearn something that we already know about the world and might be maladaptive, change a habit, something of that sort. Of course, if you give yourself experience that's exactly the same as what you've seen before, you're not going to learn anything. So you need some dissimilarity, you need some prediction error to generate learning. But as the prediction error grows, at some point, you'll get to the point where you're inferring a new latent cause. And then rather than ascribing the new experience to the old behavior, to the old habit, to the old set of events, you're ascribing it to something new. And so you'll update your original knowledge less and less. And this whole talk, I've talked about new and old latent causes as if you're deciding, is it in this cluster or in this cluster? But in our model, this is probabilistic. So you can say, 90% 10, 80% 20. And that's why this curve is gradual. So overall, my hypothesis about how latent causes affect the structure of memory is something like this. So imagine, our mental maps of the world that we learn all the time are used both for learning and for action selection, and this is what memory is for. And they may look, based on these experiments, something like this. So you have all your experiences of going to work, you read, you think. I'm thinking of academics here. I know there are people also who are not academics in the room. All these experiences are quite similar, so you might put them all in one big memory trace in your brain, right? This is what my work is like. And then comes a really unexpected event. Homeschooling, we're working from home. It's almost exactly to the day 2 years ago that COVID started. So that is the high prediction error event. And what I've shown you is that it's strongly connected to what happened before it, but it does cause an event boundary. And so then all these horrible experiences of working from home with my kids saying, Mommy, 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 are in their own memory trace that's separate from that previous memory trace, but ties strongly to the prediction error event that also is tied to what came before it. And then, another prediction error event, there's vaccine and all those new experiences. I really distinctly remember when I got my date for the vaccine and told my kids, and they were so excited. So that's the idea. And in general, what I'm saying is if we're thinking about learning as generalization, we have all these learning mechanisms that have been studied a lot in the brain, reinforcement learning in the basal ganglia with dopamine prediction errors. And I call this shallow learning because it's pretty simple learning. It's I get a prediction error, I update based on that prediction error. But what I update depends on these deep representations, these representations that say, okay, I update everything that's in the same cluster, but I keep that separate from things that are in a different cluster. And this kind of representation learning depends on both hippocampus, depends on orbitofrontal cortex, frontoparietal cortex. There's a lot of neuroscience experiments that I didn't show you today, but the idea is that the interaction of these two is what supports learning in our daily life. So I want to thank my lab, I want to thank our collaborators and our funders, and I want to thank you for your attention.